My name is Jingyi. I'm presenting my work with my advisor, Professor Ohannessian and Joe Miller. Our paper is titled Fairness Auditing in Urban Decisions Using Linear Programming-Based Data Combination. We started by looking at the Chicago 311 non-emergency dataset. These types of urban decisions are important because they influence the allocation of resources. By auditing them, we can improve cities' decision-making mechanism. What we want to measure is whether the city is being fair regardless of individuals' background. Background information like race or gender are called protected attributes. Usually, they are not available in the urban data. We need to rely on other sources to do the auditing. Some examples of these sources like census data will give us demographic information, and the tax rate or zip code will inform us about individuals' socioeconomic status. We call this data the secondary data set. To combine them with the primary data from the city, we use the proxy variable z, which links two data sets together. Previously, there is a lot of discussion on how we should measure the fairness. One popular choice is the demographic disparity DD. It's the difference of probability of success between group 1 and group 0. Under this definition, there is a next paper by Carlos and others where they give analytical formula for the upper and the lower bounds of DD without making any assumption on the relations between two data sources. However, in the Chicago 311 dataset, we cannot measure the fairness by success or not. What we have is the response time of requests across city blocks. Now the decision becomes the response time and it's continuous. We can still utilize the demographic disparity by taking threshold for the response time t. The demographic disparity now is the difference between the CDFs measured at each threshold. Then the natural extension of DD from binary to continuous is to consider the supreme difference of all thresholds. This leads us to the concept of fairness measured in terms of Kolmogorov-Smirnov distance between the CDFs. This is the definition of demographic disparity that we adopt in our paper, denoted by KSD. To calculate KSD, we need FT given A, but we never have T and A in the same place. We have the decision T and the proxy Z in the primary source, and A, the protected attributes, and the Z in the secondary source. We can look at the largest and the smallest that the KSD can be over all couplings, which is all possible FT given A compatible with both sources. And that gives us KSD plus and the KSD minus. The Carlos and others approach gives a direct way to tightly calculate KSD plus, but not for KSD minus. The main focus of our paper is to find a pragmatic way to compute the lower bound of KSD. Well, this is the exact analytical expression. When we deal with the empirical distributions derived from the data, we rewrite it as the following optimization problem. Here, the minimization over X is finding the coupling which leads to the smallest disparity, and the maximization over J is finding the difference between CDFs. All the intermediate variables are empirical expression of the two data sources. At this point, we observe that both the objective function and the constraints are convex. This allows us to rewrite everything into a standard linear programming problem. Furthermore, we managed to represent all matrices in the linear programming into sparse matrices, which gives us efficient computation for the experiments. We also showed that with enough data, this empirical lower bound will converge to the theoretical bound. Now the question is, in practice, does our method give any better bounds than Carlos' method? So going back to the original motivation of this paper, we want to study the demographic disparity of Chicago 311 data. In the 311 dataset, there are many request types like cut a tree or remove abandoned vehicle. We study them separately because they have different general processing time. For each request type, we have a set of TZ pairs, where T represents the response time to complete a certain type of requests that come from block Z. We also have the secondary census data, which gives the demographic distribution within each block. Also, we can choose any demographic splits, such as white versus others and Asian versus African Americans. Let's see the results. Looking at the first column, the images are the plots of analytical results for two types of request and race splits. In both images, you can see two curves and three horizontal lines. The curves are the bounds of Caller's method measured at each threshold. The important result is the three horizontal lines. The red dotted line is the lower bound of Caller's method. The green line is the lower bound of our method, and the blue line is the upper bound of both methods. You can see that our method does provide a tighter lower bound for demographic disparity. It's important to have a tighter lower bound for disparity because it tells us that the city could be pretty unfair even under the most optimistic setting. To see how often we see the improvement between the lower bounds, let's look at the second column. We run the same experiments for other request types. We can see that for two different race splits, more than half of the time, our method will give us a tighter lower bound. The other advantage of our method is that it can output the coupling FT given AZ that achieves this lower bound. So we have the disparity on the block level. In this Chicago map, we draw a heat map of demographic disparity for the no water complaint request type. The blocks are colored from green to red in order of increasing disparity. We can see that there are certain amounts of red blocks that have high disparity even under the best coupling. That's all I want to talk about today. Thank you so much for listening.